today we are going to be talking about types of forces. Then we're going to go through, we're going to talk about a way of representing all of the forces that are acting on an object called free body diagrams. So first off, let's remind ourselves what a force is. A force is a push or a pull that can make an object accelerate. And we know Newton's first law. Raise your hand if you can remind the class of Newton's first law. Yossi, remind us of Newton's first law.
I remember it, but I wanted to make this.
Okay, you go right ahead.
I can tell you in a minute.
Okay.
Isn't it like objects in motion sort of stay in motion?
Mm-hmm. Objects in motion will remain in motion. What about objects at rest?
On a stair?
Until an unbalanced force.
Yeah, until an unbalanced force applied. Thank you, Joaquin. Thank you, Yossi. So things in motion stay in motion, things at rest stay at rest until an unbalanced force is applied. So let's talk about what these forces could be. And then we're going to talk about ways in which they might be balancing each other out. So the first, what you're going to want on this sheet of notepaper, you're going to want 3 columns. The first column is just going to be for the name of the force. So the first column,
Should these 3 columns like fill up our entire paper?
yes. But the first 2 columns can be pretty small. So the first column is just going to be for the name of the force. So for example, gravity is a force that we've been talking about a lot. The second column is going to be an abbreviation that we use to represent that force. Because of course, physicists are super lazy. We never write out full sentences. We always want to have an abbreviation that we can use. An M for mass, an A for acceleration, etc. And the third column is going to be the description. So your description should be taking up most of the space. That should be the biggest column. Okay, so you're going to have 3 columns. I'm going to actually erase this because I have a lot of forces to get through and I want to have space to write them all. So, the first force that we ever talked about in this class was gravity. And we know a lot about gravity. We know that it is a force. We know that it pulls. Remember, forces can be either pushes or pulls. Gravity is a force that pulls objects towards the nearest, biggest thing. So our abbreviation for gravity is going to be a capital F for force, and then a little lowercase g that means the force of gravity specifically. This is also known as weight. So it's sort of also known as weight.
Wait, Hannah, what was the second column again?
The abbreviation that we're going to use to represent that. So I don't have to write out the word weight or write out the force of gravity. I can just write a capital F for force with a little g next to it as a subscript. And that means I'm talking about the force, which with capital F is of gravity specifically. And we know the following things about gravity. It is a force that pulls objects towards the nearest, biggest thing. By biggest, I mean most massive, as in literally having the most mass. Now, you all are going to spend most of your lives, probably all of your lives, on planet Earth. So for most every problem you're going to deal with, the force of gravity is going to be pulling things down towards our planet. It's not just going to be the nearest, biggest thing that you're dealing with in any given situation. But you might, in theory, be dealing with a situation where they're talking about things happening in space where gravity might be pulling something in a different direction. Right? Where there's a different nearest, biggest thing. We feel okay with you. You understand that gravity exists. It's a force. That feels okay?
I have a question.
Yes. What? Yes.
Is the F for force and the little g for gravity?
Yes. That's exactly correct. And you'll see when we talk about other forces, they follow a really similar pattern for how we do abbreviations. So, let's say we have an object sitting on a table. Right? I see Lisa's binder just right there on the table. Is gravity pulling on this binder right now?
Yeah.
Yes. Is the binder currently accelerating?
No.
No, it's not accelerating.
Oh wait, no.
right? You know, you could say it's moving. It might have velocity. You could say it's moving at 1,000 miles an hour as the Earth spins on its axis, but it's not accelerating. So, if we know that it's not accelerating, that means that it must have balanced forces. Because if the forces were unbalanced, it would be accelerating. So if we know that the forces acting on this are balanced, and that gravity is pulling it down, why isn't it actually accelerating downwards? Yossi?
Because the table is keeping it from going downwards and it's pushing it up.
Yeah, there's a different force from the table that's pushing it up. Now that force has a name. We call that force the normal force. I don't know where the name normal force came from, but it's a fitting name because the normal force is a thing that we just kind of all take for granted. So we call this the normal force. And the abbreviation for it is a capital F for force, with as a subscript, which means just a little tiny letter, a capital N for normal. So Fg for gravity, Fn for normal force. If you're doing this on your piece of paper, by the way, I would like skip a line so you can really easily see each individual force and they don't kind of blur together. Just keep it nice and tidy. I'm a little bit cramped here because I'm trying to fit it all on this board. You've got more space than I do. So this is the force of surfaces pushing back up on objects. Force of surfaces pushing back up on objects. This force is actually caused, weirdly enough, by something called electromagnetism. Right? It's a type of magnetism that's keeping this working. And the reason why, caused by electromagnetism, is that all of your tables and the floors and things, they're made out of molecules, and those molecules are made out of atoms, and those atoms have electrons on their outermost edge. And every electron is basically a tiny magnet. Electrons repel each other. And the electrons in the table repel the electrons in the binder and keep it from falling through. So, fun fact about atoms, atoms are actually mostly empty space. The actual particles that make up an atom are tiny compared to the amount of space that an atom takes up. And yet, you know, you can't pass your hand through the table. We don't just phase through objects. Because there is this normal force, this electromagnetism that repels things. Now, there's some really cool things about the normal force. One of the cool things about the normal force is it's kind of exactly as strong as it needs to be. Because here's the thing, I can push on a table. And if I push down on a table, right, I push down on it, there's, you know, my hands have some weight to them and the hand pushes back. But the harder I push down, the more my electrons get closer to those electrons. And as my electrons get closer to the electrons in the table, the magnetism is stronger the closer things are. So the closer I try to force my electrons to the electrons in the table, the stronger that normal force can push back. And that means that, like, here the normal force is balanced with the strength of my hands. If I push harder, it's balanced. As hard as I push, it stays balanced. Right? Very cool. So the normal force will tend to balance out gravity. It's really good at balancing out gravity. There's some other things that I want to note about the normal force. I will say I'm now getting a little bit more into the strictly high school level, so this part you're not going to be tested on or anything. I am just going to give you a little preview of things that you'll deal with in high school. The normal force is perpendicular to the surface, which means, like, if you have a flat surface, the normal force points straight up. Gravity, of course, is pointing straight down. So what that means is if the surface is flat, then the normal force is exactly equal to the force of gravity, and it balances it out. But if the surface is at an angle, then the normal force is pointing perpendicular to the surface. The normal force is pointing like that. But gravity is still pointing straight down. So now they can't actually perfectly balance each other out. That's why, my pen can just sit here on a flat surface, but as soon as the surface tilts, gravity is stronger than the normal force and it can fall. So that's the technical explanation for why things roll off when they're at an angle and not when they're flat. All right. Any questions about the normal force? This one's going to come up a lot. Anytime something is on a surface, anytime someone's standing on the ground, or there's something underneath them that's balancing out gravity, the normal force is going to be in play. All right. Our next force is the only force in this list that has any intentionality or purpose or will or mind behind it. We call it the applied force. Most of the forces on this list just happen, right? No one has to, the planet Earth isn't actively reaching up and yanking things down towards it, right? The table isn't actively thinking about pushing up on things. But when your cat walks up to a glass on the edge of the table and goes, heck this, he knocks it off, that cat decides to push it. This is the name for forces that somebody or something decided to push or pull. So this is our applied force, and its abbreviation. You want to guess?
FA.
Yeah. So we use a capital F and a capital A here for the applied force.
Is there a reason G for gravity as well? Is there another G?
There is another G. We use a capital G for something called the gravitational constant, which is a number that's used in certain equations to calculate how strong gravity would be between two objects.
Couldn't you just do FGC then?
I mean, that's adding a lot of
That's so
We
much.
try not to add multiple letters that mean a single thing. It's not to say it doesn't happen. We try not to, because then how would you know if it was a single thing that's GC or one thing that's G multiplied by something else that's C, right? So we try to avoid that. But yeah, there are certain conventions about which things we capitalize and which things aren't capitalized, and there's kind of just its own little grammar that you sort of have to learn. And as with all things, it gets easier the more you use it, the more intuitive it becomes, right? So at first it's just a weird set of rules. This one's capitalized, that one's not, and then eventually it just becomes normal in the same way that capitalizing the letter I in a sentence is normal. Why do we do that? That's entirely arbitrary. We just do. All right. So the applied force. This is when a person / creature / machine.
Can I just write person / creature?
Sure. Pushes or pulls. Okay. So this is the only one that has any set of will behind it. It's a push or a pull on it. You could use this for your cat knocking a glass off something. You could use this for the fan on those fan parts we were looking at. Right?
Does you turn on the fan?
Yep. So that counts as an applied force. Right? Anything that has any kind of agency or will behind it is going to be an applied force. Fun thing about this one, it could be a push or a pull. Right? You can push on things, you can pull on things. So it could be either. Whereas gravity's always going to be pulling on things. The normal force always pushes on things. But this one could be a push or a pull. So that's our applied force. The next force we're going to talk about is the one we were investigating yesterday. So I know this feels like maybe a lot of information all at once, but hopefully all of these things we've referenced a little bit already, so you should have some measure of familiarity with them. The next one is friction. And for friction, we use a capital F for force and a lowercase f for friction. There are a million different kinds of friction. You will hear this referred to as static friction, which is when something's just sitting there and it's hard to get it started moving. People will talk about kinetic friction, which is how much friction there is when something is sliding against something else. Or rolling friction, which is like kinetic friction, except now you've got something on wheels or rollers and it's a little easier to move it. You'll have people talk about drag or air resistance. But basically, any time we have an object that's moving, and as it's moving, it's like hitting particles or hitting a surface, it's rubbing against things, and that act of rubbing against things is going to slow it down. That's friction. Yes, Emily?
What does the F stand for?
So the capital F is for force. The lowercase f here is for friction. So this is the force of friction. This is the force of gravity, the force of the normal force, the force of the applied force, the force of friction.
For all these abbreviations, is force always at the top?
Yes. All right, so friction. The things you should know about friction. Friction always opposes motion. This is a force that opposes motion. That means that friction is always either going to be slowing something down or stopping it from moving in the first place. So we can only ever slow things down, never speed them up. And there's many different kinds of friction that we can have. So air resistance is what we've really talked about. That is a type of friction. Air resistance is a type of friction. So some other terms for friction. We'll talk about drag, air resistance. People will talk about static friction, kinetic friction, rolling friction. How strong friction is can vary slightly depending on whether something is sliding across a thing, whether it started moving or it's already moving, whether it's on rollers or not, etc. All those things can impact how strong the force of friction is. But the important thing here is that it's a force that opposes motion. It's always going to be trying to slow you down. That's what friction is. So we're gonna think of air resistance as a type of friction in this class. All right. Now these four forces: gravity, the normal force, the applied force, and the force of friction, they're gonna come up a lot in our class. I'm gonna do sort of a speed run of some forces that you might see come up a little bit less often. So when you have things that are hanging from a string, like imagine you're hanging off a rope, gravity's pulling you down, but you're not falling because the rope is holding you up. There is a name for that force. We call it tension. So tension, Ft. We use a capital T for some reason, and that's things on strings.
Do you have a pencil sharpener, Hannah?
I do. There is a pencil sharpener right there, but you're also welcome to just grab a fresh pencil and then sharpen it the next time there's a break in the class. If you've ever floated in a boat or on a little floaty thing, right, you know that gravity's still pulling you down, but something is pushing you up. Has anyone here ever done the thing as a kid where you have like a beach ball in the water and you like try to shove the beach ball underwater and it's really hard and if you let go it goes shooting up? The force that makes it go up is called buoyancy. Yesha?
After right, would you mind doing that?
Yes, I will give you a moment where if you want to take a picture of it beside you.
It's like we're using a cube
So
and stand on it.
B is buoyancy. So that's for floating things. That would be, whether it's a helium balloon or a beach ball floating in a pool. We use buoyancy for that. Another one that'll come up is magnetism. For that we use Fm. And that's magnets. Magnets are fun. They can be a push or a pull. This is not an exhaustive list. There are more types of forces than this. Alternatively, you could say, oh, actually, a lot of these things boil down to electromagnetism. Really, a lot of these things are secretly just magnets. But the important thing is having some words to describe these forces. Okay? This is not an exhaustive list. There are more types of forces than just these. But this is enough to get us started. All right, take a moment, finish writing down whatever you need to. If you want to take a quick snapshot, you can take a quick snapshot. And then we're going to move on to our next topic, which is free body diagrams. So Emily, you can actually stop this video, and we'll do a fresh one for the other one.